We're given the function f of x comma y and asked to find the partial derivatives and evaluate at the given point. Notice how we have two first-order partial derivatives and two second-order partial derivatives. Let's begin by reviewing what the first-order partial derivatives tell us about our surface, as well as how to find them. The first-order partial derivative of a function of two variables tells us the slope of the tangent line at a given point in either the positive x or positive y direction. This measures the rate of change of z, or our function f, with respect to x, or the rate of change of z, or f, with respect to y, based upon which partial derivative we're determining. To determine the partial derivative with respect to x, we consider y a constant and differentiate with respect to x. To determine the partial derivative with respect to y, we consider x a constant and differentiate with respect to y. So going back to our example, we'll begin by determining the partial derivative with respect to x. So we'll differentiate each term with respect to x, treating y as a constant. So the derivative of 5x squared with respect to x would be 10x plus the derivative of 3x squared y cubed with respect to x, treating y cubed as a constant. So we'd multiply by 2 and then subtract 1 from the exponent on x, which would give us 6x to the first, or 6x y to the third. And then the derivative of 3y to the fifth with respect to x would be 0, again because we're treating y as a constant. So here's our first order partial derivative with respect to x, and now we'll evaluate this at our point. Notice how we only need the x and y values, so we'll substitute 1/2 for x and 1 for y. So we'd have 10 times 1/2 plus 6 times 1/2 times 1 cubed, which would give us 5 plus 3, which equals 8. Which means the slope of the tangent line in the x direction at this point is positive 8. And let's look at this graphically. Our surface is graphed here in purple. The point we're considering is this red point, and this blue line is a tangent line at that point in the x direction, which is in this yellow plane, which is parallel to the x-axis. This arrow here indicates the positive x direction. Notice as we move in this direction from our point, the line is moving uphill, and it has a slope of positive 8. So this is what the partial derivative with respect to x is telling us about the tangent line at that point. Now we want to find the partial derivative with respect to y, so we'll differentiate with respect to y, treating x as a constant. So the derivative of 5x squared with respect to y would be 0. The derivative of 3x squared y cubed with respect to y, we would multiply by 3, so that would give us 9. Then we'd have x squared y to the second, because we subtract 1 from the exponent of 3 on the y, and then plus the derivative of 3y to the fifth with respect to y would be 15 y to the fourth. And now we'll evaluate this at our point. So again, we'll substitute 1/2 for x and 1 for y. So we'll have 9 times 1/2 squared times 1 squared plus 15 times 1 to the fourth. So here we'd have 9/4 plus 15, 15 over 1. Common denominator would be 4. So we have 9/4 plus 60/4, or 69/4. So the slope of the tangent line in the positive y direction at this point would be positive 69/4. Let's take a look. Again, here's a graph of our surface. Now the plane is parallel to the y-axis, and this arrow here indicates the direction of the positive y-axis. So notice how the tangent line is graphed here in blue. Notice if we move in the positive y direction, the slope of the tangent line would be positive 69/4. Notice how it's going uphill very quickly. Now let's review what the second order partial derivatives tell us about a surface and how to find them. If the second order partial with respect to x is positive, then our function is concave up in the x direction. If the second order partial with respect to y is positive, then the function is concave up in the y direction. And of course, if these are negative, this would indicate that the function would be concave down in the x and y directions. The mixed partials, indicated using this notation here, tells us how a partial in one variable is changing in the direction of the other. So the partial derivative of f with respect to x and then with respect to y tells us how fast the rate of change of f in the x direction is changing as we move in the y direction. We could also say this tells us how the slope of the tangent line in the x direction is changing as we move in the y direction. And the mixed partials are equal if both mixed partials are continuous on an open region for every point in that region. So to find the second order partial with respect to x, we want to differentiate with respect to x twice. So we'll take our first order partial with respect to x here and differentiate with respect to x again, treating y as a constant. So the derivative of 10x with respect to x would be 10 plus the derivative of 6x y to the third with respect to x. So we're treating y to the third as a constant. So our derivative with respect to x would just be 6y to the third. And now we evaluate this at our point. So we would have 10 plus 6 times 1 to the third, which equals 16. So notice how the second order partial with respect to x is positive, or greater than 0, meaning from this point, if we move in the x direction, the function is concave up. And let's go ahead and verify that. Notice from this view, where the yellow plane is parallel to the x-axis, we can see that the surface is concave up in the x direction. And then finally, we want to find the partial derivative with respect to x, then with respect to y, which means now we'll differentiate this first order partial with respect to x with respect to y. So we'll treat x as a constant. So the derivative of 10x with respect to y would be 0. The derivative of 6x y to the third with respect to y would be 18x y squared. So let's evaluate this at our point. So we'd have 18 times 1/2 times 1 squared. So this would be 9. And again, notice how this is positive or greater than 0, which means the slope of the tangent line in the x direction as we move in the y direction is increasing. And before we go, let's go ahead and find the other second order mixed partial, the partial derivative of f with respect to y, then with respect to x, which means we would now find the derivative of this partial derivative with respect to x, so we treat y as a constant. So the derivative of 9x squared y squared with respect to x would be 18x to the first y squared, or 18xy squared. And the derivative of 15y to the fourth with respect to x would be 0. So notice how our second order mixed partials are equal. I hope you found this helpful.